So hello everyone. So today we'll start our fourth tutorial class for the course of Fundamentals of Statistical Thermodynamics. So before going to the content of today's class, let me just briefly recap the things that we've discussed in the last class. So So on the last class, we start our discussion from the definition of the total energy. Okay. So, so our main goal was to get our expression for the internal energy. But in order to get that, the first thing that we need is the how we can get the total energy for the system. Because if you once know the total energy of system, using that we can easily evaluate the internal energy. Okay. So how do you get the total energy? Let's suppose this is a typical energy diagram of our system. So each of the energy levels are associated with some energy E1, E2, E3, E4, and there are a number of particles N1, N2, N3, N4, N5 like this, which is associated with each of the energy levels. Now, for this kind of a system, to know the total energy, this is basic formula. So total energy was E is basically equal to Ni into Ei. Okay. So the energy of each of the level is into multiplied with the number of particles resides into the energy level. Okay. Now from here we have substituted. So this Ni thing we know, right? We have from the Boltzmann distribution we know that each particles are basically distributed in the energy states by following this Boltzmann distribution, right? So Ni by n would be equal to e to the power minus beta Ei by q. Q is the partition function. So now if we substitute this thing here, we get the total energy E as n by q summation over Ei into t to the power beta Ei, right? So this is the total energy. Now we can write it in a more algebraically simpler way by writing this whole thing as a derivative of e to the power beta Ei, right? So we can write it like this: n by q equal to summation over I d beta of e to the power minus beta Ei. Okay. So this e to the power beta Ei summation is nothing but it's the partition function, right? So it will now become n by q equal to dq by d beta. So q is basically summation over I to the power beta Ei. So substitute this thing here. So after doing that, you get the very nice looking expression for the total energy of a system, right? So by observing this expression, you can easily tell that once you get the correct form of the partition function of the system, by using that only you can easily get the total energy, because just by doing the derivative with respect to beta, and beta is nothing but 1 by kV2. It's a very formal way of writing the temperature of the system. Okay. So after that, we have discussed some problems on it, and okay. So yeah, now since we get a hand on the total energy, now using this we can easily calculate the internal energy. So the internal energy is internal energy is basically U naught plus E equal. So this U naught is basically zero point energy. Okay. So to basically add the 0 point energy to the total energy of the system in order to get the internal energy. Okay. So now after writing the expression of the total energy here, we will get the expression of internal energy as U equal to U0 minus N by Q del Q del beta constant energy. Now, for particular case, let's suppose that for a case of an ideal gas where the gas is, let's suppose, is trapped inside a 3D box. So for that specific case, we can also calculate. We can further simplify this expression actually. Okay. So you know, right? For a case of a particle, if it's trapped inside a box and it's a free particle which can move freely inside the box, in that case, we know the partition function is can be written by like this, right? Q equal to V by lambda Q, where V is the volume of the box and lambda is the thermal wavelength. And the expression of lambda was basically lambda equal to beta square by m. So if you substitute that expression of Q here, you will get Q minus U0 equal to minus N by V lambda Q del V by lambda Q by del beta. If we do this calculation of this derivative, you will get Q minus U0 equal to 3n by 2 beta into 1 by lambda into lambda. This is equal to 3n by 2 beta. So U minus U0 would be U would be U0 plus 3n by 2 beta. So this is basically the expression of the internal energy U. And for the case of an ideal gas, this can be this 3n by 2 beta can be written as 3 beta, 3 by 2 kBT into n. And you can know it's nothing but a mole into Na. Okay. So it can be written 3 by 2 Na into Kb into T into small n. So Na into Kb is nothing but the ideal gas constant is R, right? R NR. Okay. So it will now become, the expression will become U equal to U0 plus 3 by 2 NR. Okay. The expression of the internal energy. And from here you can easily calculate several other things. So one of the most important things that you can calculate from if you get the expression of CV, expression of internal energy. So that quantity is basically known as the heat capacity or specifically a constant volume. So heat capacity at constant volume is known as CV. Expression is del U del T at constant volume. If you do this derivative del U del T, you get 3 by 2 NR of CV. Okay. So yeah. So And this expression of Cv, this expression is basically comes from the first law of thermodynamics, is equal to du plus dw, or dq by du plus pdv. So at constant volume, we know dq would be equal to du. The Cv, we know Cv is nothing but dq by dt at constant volume. This thing can write as du by dt at constant volume. The fundamental definition, this comes from the fundamental definition of Cv, that is the amount of heat required to basically increase the temperature of the sustain by unit amount. So here this amount is dt, and the heat is taken by dq. So dq by dt is the basically is a formal definition of the specific constant volume. Okay. So we have done some problems about it after doing that. Next, we have defined the entropy, right? So entropy, for a reversible process, we know the entropy is related by the change in heat Q reversible divided by T. So at constant volume, this dq reversible nothing but du by T. So, and you know that u equal to u0 plus summation over I ni ei. So gu would be ni dei and summation over ei dni. Okay. Now we have substituted this thing here and we have done some calculations. After doing that, we use similar say many concepts of like the configuration, the weight, all the formulas of weight, with weight are mostly probable. So after using all those mathematics and all those assumptions here, we get the change in the expression of changing entropy like this: A equal to summation over I. So no summation is there. A into G of log W. Now from here, S will be A into log W. This is the expression of entropy we got. But this for a system, if you want to calculate the entropy by using this formula, in order to do so, you basically need this configuration of the possible configuration of the system W. So that is not very convenient all time to calculate this W thing, right? Because it's also a very large number to calculate. Okay. So there is also a formula, also a way you can say by which we can write this expression of entropy by using only the definition of thermodynamic variables like internal energy and partition function and all. Okay. So how to do that? So for that, use this definition ln W in the first class. In the very first class, we know ln W is nothing but n into ln n minus factorial I ni into ln n. This is basically comes from the discussion of the weights of a particular configuration, right? That you have done in the very first class. So from here, from this quantity, you substitute in this expression of entropy. After doing some mathematics, you'll get this kind of expression. So ln W will now become 1 by T, sorry, E by T plus NK ln Q. Okay. So E is, so if you substitute E is nothing but E we know, E plus U0 is basically U. So you can write this relation here, you can substitute this relation here. So after doing that, you will get S equal to U minus U0 by T plus NK ln Q. So this is the expression of the entropy of the system. Yeah. But this is a very convenient way to calculate the entropy. So for here, you just only need the information of the internal energy or the total energy and the partition function. Okay, so by using that two thing and using this particular expression, you can easily get the value of the entropy. So now we'll start with some problems now. Okay. So for today's class, so the statement of the problem is like this. Consider a system with 4 energy levels. So ground state is having energy at E0 equal to 0, and it's triply degenerate. Okay, so there is degeneracy associated with each of the energy levels. So it's triply degenerate. That means G0 is equal to 3. The second is E1 is doubly degenerate. So G1 is 2. Third is second excitation, E2 is non-degenerate. So there is no degeneracy associated. Non-degenerate. The degeneracy of G2 is basically 1. And 3 is third excited state is triply degenerate. Okay, 3 is triply degenerate. So G3 is 3. Okay. So this is a description of the problem, and you are required to find out for n non-interacting identical particles, derive the expression of the internal energy and the entropy. Okay. So the problem is for n non-interacting identical particles derive the expressions of the internal energy Qg and the entropy. On the entropy ST2. So yeah. So we know the basic strategy to solve this kind of a problem, and that is the finding first or write the first partition function for the system, and the single particle, since there is only one part, n numbers of particles are there, right? So first we'll write the partition function for a single particle, that is a q, small q, right? And by using the formula of the internal energy, we can get the total for n particle, we'll get the total internal energy, right? So first we'll have to write out single particle partition function. Q is equal to summation of J G C between the beta E 0. Now, so G0 into the beta E0 plus G1 into the beta E1 plus G2 into the beta E2 plus G3 into the beta E3. So E0 is 0, we know, and the degeneracy is 3, so 3 plus G1 was 2 to the power beta E1. G2 has single degeneration to the power beta E2, and G3 is again 3, I guess, yeah, 3. So 3 into to the power beta E3. So this is the single particle partition function. Now for n numbers of non-interacting particles, we know, we like previous to previous class, we have already calculated the internal energy. The expression looks like this. Basically U minus U0. The internal energy here there is means that you have not U should be equal to U0 plus minus n into del beta of ln Q. Okay. So this thing also you can write it like this: U0 minus n by Q del beta. Okay. So yeah. So first thing you have to calculate is del Q del beta. Okay. Del Q del beta of 3 plus beta E1 plus beta E2 plus 3 beta E1. So to the derivative, we will get to give you minus 1 epsilon 1 to the power beta E1 plus E2 to the power beta E2 plus epsilon E3 to the power beta E3. So now U is so you got the expression of dq d beta. So U is basically U0 minus, so minus is a minus, so dq d beta also has a minus, so minus will become plus. So n into 2 epsilon 1 to the power beta E1 plus epsilon to the power beta E2 plus 3 into epsilon 3 to the power beta E3 divided by Q. Q is this whole thing 3 plus 4 to the power beta E1 plus e to the power beta E2 plus 3 into the power beta E3. So this is the expression of the total energy of the system. Okay. Total internal energy of the system. Okay. So you got the internal energy. Next our work would be to find out the entropy. The entropy expression, you know, is the expression of the entropy. So this is an expression is equal to U minus U0 by T. This one is equal to U minus U0 by T plus Nk by ln Q, right? So it's going to be U minus U0 by T plus Nk ln Q. So yeah, so U minus U0, you know, from here you can get U minus U0. So it's equal to U minus U0 will be n by 2 into U epsilon 1 e to the power beta epsilon 1 plus epsilon 2 e to the power beta epsilon 2 3 into epsilon 3 to the power beta E3 divided by Q, that is 3 plus 3 into the power beta E1 plus 3 to the power beta E3 plus 3 into the power beta E3 plus Nk into ln Q. So ln Q, yeah, ln Q also there. Ln Q is this thing. So ln Q is ln to 3 plus 2 by beta U1 plus beta U2 plus beta U3. This is the expression of the entropy part. Okay. So now, so now the next thing that we will do is that for a Boltzmann distribution, we will from the distribution of the particle from let's suppose for a two-level system, from the distribution of the particle from those from that particular two-level system, we try to find out how can you get the expression of T. I mean expression of the temperature. Okay. So let's suppose there are two energy levels over here like this, E and 0. And first excited state, that is the energy E, the energy level is energy E that has a particle number n plus, the ground level has n minus. Okay. So, you know, according to Boltzmann distribution, the ratio of population in a global system that is given by n plus divided by n minus equal to epsilon PVT. The E is nothing but the basically E is supposed to be delta E, that is the difference in energy. Here the delta is equal to E minus 0, that is E. Okay. Now, so from this expression, so in the right hand side of the equation, you can see there is already the temperature is already there. So you have to write this whole expression in terms of temperature. So the easiest way to do that is to take log of both sides, n plus by n minus. Take log of exponential, it gives it will return back the exponents only. So E by KBT. So from here, T would be E by K divided by log of n minus by n plus. So here, so we invert the ratio because we have absorbed the negative sign inside the log part. So that's why this thing inside the log gets inverted. Okay. So this is basically the expression of the temperature we got. Okay. Yeah. So as you can see, so for a two-level system, if you get the values of or get the expression of the population on the ground state as well on the low energy state and high energy state, and so from using this expression, basically substituting all these things into these expressions, you get the particular temperature of that particular system. Okay. Now, one of the important observation from here is that, so in this thing, this in the denominator part, ln n minus by n plus. Okay. So if you do this like this, if you put n minus, that is the low state population is smaller than the n plus, that is the upper state population. If you do that, you will able to see this temperature. This long term n minus by h plus, this will become negative. Okay, because the upper part will be lower, lower part will be higher. Sorry, numerator is lower and denominator is higher. So in that case, this inside this ln, there will be a fraction term involved. So if fraction term is there inside a ln, so it will give you a negative number, right? Fraction term that is less than 1, right? That is there, that will be there inside the ln. So if you do the ln of those values that is lesser than 1, in that case this gives you negative values, right? So yeah, so that means the temperature will become also negative. So this is a basically theoretical concept by using this in which you can get the negative temperature of a system. So yeah, so there are some properties uh, of a system which is in negative temperature. So first is all the statistical thermodynamic expressions we have derived applied to t less than 0 as well as t greater than 0. So in both the cases, all these thermodynamic expressions are valid. The states above t less than 0 are not in thermal equilibrium. Okay. This is also a key point, and therefore therefore they do not rely on the equilibration of temperature thing. Okay. E with the surroundings. What the thermodynamics says is that this particular case for achieving this negative temperature, you cannot basically achieve a negative temperature by using a finite numbers of steps. Okay, what the prohibits achievement of absolute zero in a finite number of steps. These are some key properties of the say of a thermodynamic of a system which are in uh, uh, for a system which is in negative temperature. Okay. So how to we'll first give some overview that how we can basically get the temperature at very low. Okay. So We'll discuss a multi-step process. So using this, one can achieve very low, close to 0 Kelvin temperature. So for that, so yeah, so first, how we can do that? So we'll consider the case for a magnetic system. Okay. Now, if you plot, let's suppose that you have two types of system. One is magnetized, and one is unmagnetized. Okay. So for a magnetized system, for a magnetized system, the most of the magnetic domains are basically aligned in a particular direction, right? This is magnetized. And this is unmagnetized. For unmagnetized case, these domains are very random. Okay. Now, so if you draw the entropy versus the temperature for a case of for both the case for a magnetized as well as for an unmagnetized system, you will see it will show it's like this. So as you increase the temperature, the for the case of unmagnetized state, it's unmagnetized. The entropy increase at a higher rate with temperature compared to the magnetized system. Okay. So now let's suppose your system is in A. So now if you shift between this magnetization unmagnetization state to magnetized state in a step-by-step process like this, from unmagnetized, you do this isothermal demagnetization process, during which you basically demagnetize the system and as well as maintain a temperature fixed. Okay. So this thing geometrically can be denoted inside the figure by using a vertical straight line, right? So this is the process known as isothermal magnetization. Sorry, yeah, isothermal magnetization. Because it basically magnetize the system. Now from here we go to A to B to B to C. Now this B to C is, you can see here, the entropy remains constant, but the system becomes magnetized to unmagnetized. Okay. So this particular process is known as adiabatic demagnetization. Adiabatic demagnetization. Okay. Now from A to B, B to C, then again C to D, then D to E. Okay. So like this, if you do this step again and again and again, after a certain point of time, you will basically bring this temperature of the system very low. I mean almost close to zero. But exactly zero you cannot get, because for that you have to do this step this step like isothermal magnetization and adiabatic demagnetization. These two steps over and over and over again, an infinite amount of time, which is not practically possible. So this is basically a process that in experimental physics people use. Like in experiments, there are a lot of methods or experiments are happening that require the temperature to be very low, close to zero temperature. Like let's suppose something related to superconductor, something like that experiments happening on. For that case, you need a very low temperature. So to do that, thermodynamic consistency, this is a kind of a multi-step approach people usually take. Okay, so yeah, so this is two processes are basically. One is the isothermal magnetization, and second is the melting. This is do this again and again and again. Cyclic way. Okay, first do this, then again this, then again this, then again this. So in one to way, if you do that, so you will basically bring down the temperature of the system in a close to a very low value. Okay. Now we'll do a small problem on this. So the problem is mm, level 0 and E with degeneracy G0 and G1 system in contact with bath at inverse temperature beta less than 0, then we have to find the excited divided by ground population ratio. Okay, so we know that the formula is like this: n1 by n0 is g1 by g0 into e to the power beta e, right? Now the if temperature is negative, so that means this beta is negative, inverse temperature, right? So beta is less than 0, beta is less than 0, then e to the power minus beta e would be greater than 1. So that means if you plug it in here, so it will give you n1 by n0 greater than 1, which is n1 is greater than n0. Okay, so that means, so what basically happens is here is that, so if two levels are there, n0 e0 and e, so each level, the 0th level has population n0 and e level has population n1. So in that case, so this condition shows that the population at the excited states is higher than the population ground state. That is the phenomena is expected for a system which is in inverse temperature, right? So let's, like, if let's suppose g0 is equal to g1, let's suppose this epsilon k is 300 Kelvin and temperature, let's suppose, is minus 150 Kelvin. Now if this information, if you put it here, you will get n1 by n0 equal to e to the power beta, so e by k is 300, so minus 300 by minus 150, right? So it will give you e square, so e square is n1 into 7.39 of n0. So as you can see, the population of this first excited is almost 7 times larger than the population at the ground state. Okay, so next we'll discuss a problem on that partition function. Okay, for a two-level system. Okay, so as we have discussed that for this case of the negative temperature or when the temperature becomes very high or the temperature becomes very low. For these cases of this two level system, we will basically check different types of thermodynamic quantities. Okay, what will happen to those quantities also? Okay, so let me write. When the temperature becomes negative and infinity. So first let me write the partition function, that is q. Q is summation over gj e to the power beta ej. So yeah, so if you sum over of all the energy levels, it will give you gj e to the power beta ej, summation over all j, so all of the energy levels. So yeah, okay, so beta we can write it like this also, ej by kbt. Okay, now it's fine. So now since we are like varying the temperature, so it's better to write this expression in terms of temperature, not in terms of beta. Okay, so yeah, so now so for two level system we know 0 and d. So q would be so the degeneracy of first excited, let's suppose it's g0 and this is g1. So g0 e to the power beta into 0, or 0 by kbt, 0 by kbt plus g1 into to the power e by kbt. So it will become g0 plus g1 into the power e kbt. It's the q, the partition function q. Okay, now if you put t tends to 0, very low temperature, q will become 1 plus e to the power minus infinity. So this gives, so t is basically 0 means what happened, e by kbt. So t very 0, so e by some 0 is there, so it will become to the power infinite, right? This thing, so to the power infinite, so e to the power minus infinite is nothing but 1. So sorry, e by 1 by infinite is 0, right? So q will become 1. Okay, so next thing is that what happened is that t tends to infinite. So if you put t tends to infinite, it will become q into g0 equal to g0 plus g1 e to the power e by infinite. So g0 plus g1, so 1 by infinite is nothing but 0, right? 0, so e to the power minus 0, so g0 plus so g0, if g0 is 1, in that case 1 plus 1, g1 let's suppose is also 1, so 1 plus 1, that will become 2. So for the context, let's consider g0 is 1, g1 is 1. So all the states are all the two energy states has no degeneracy. Okay, for the time being. Now, okay, so now if you what happen, so this thing we consider when we basically increase the temperature. This is basically we are approaching the temperature towards zero from the positive side. Okay, now let's see what happens if you decrease the, if you tends to zero temperature from the negative side. That means from negative direction you are approaching towards zero temperature. Okay, so in that case what will happen is that Q will become 1 plus e to the power plus some epsilon by 0, right? Since it's coming from negative direction, right? So the temperature is negative, so negative negative will become positive, so e by 0 it will be some positive, so it will be a very high number, right? 1 by 0 is like infinite, so it will become very high. Similar way, if you approach the infinite temperature from the negative direction, okay, just like the case where the previous case we approach the temperature from the positive, from the negative direction towards zero. Now we are going towards infinite, in the from the negative infinite direction. In that case Q would become 1 plus e to the power, here also plus e by infinite. That is also nothing but 1 plus 1 by infinite is 0, right? So e to the power 0, that is 1 plus 1 equal to 2. So now if you plot this partition function, it looks like this. So if you decrease the system from negative 2, it will negative infinity will goes to towards 2, and if you increase it more towards 0 from the negative axis, it will become very high, so it will tends to infinite like this. Similar way, so if you comes towards 0 from the positive side, you know its Q would be tends to 1, and from here also if you increase the temperature towards infinite from the positive direction infinite, it will moves like this to a constant value. This is typically the diagram. So this is the partition function on the y-axis. So this is how the typically the partition function behaves for a two-level system. Graphically we have seen. Now we'll move towards the case of the internal energy. Okay. So next we'll discuss the internal energy. Okay, so let's first write the expression of the internal energy. Okay, so for our two level system, so next will the internal energy. Okay, so Q already know, 1 plus e to the power beta e, u minus u0 is basically n by q del q del beta, that constant volume. So u minus u0 would be minus n by 1 plus e to the power beta e into minus e into e to the power minus beta e. Then beta e minus minus will become plus, so 1 plus e to the power minus beta e. So e to the power minus beta you can multiply in numerator and denominator, so in that case it will become Ne divided by 1 plus e to the power minus beta e. This is the expression of the internal energy. Okay, now so we got the expression for the internal energy for two level system. Now our next job is to plot it out for different cases. Okay, so for t tends to, if t tends to 0 from positive side, in that case beta will be tends to infinite, so Ne will be become 1 plus e to the power minus infinite, so 1 by infinite would be 0. Sorry, it would become b to the power plus, yeah, so yeah, this will be plus. And now it's fine, so it will become plus infinite, so some Ne by infinite, so this basically tends to 0, right? So u is basically tends to 0 for t if t approaches to 0 from positive direction. Now we'll discuss if t approaches plus infinite, in that case beta tends to 0 and Ne by 1 plus e to the power 0 into e, so it will become Ne by 2, so u will become 0.5 Ne. Okay, if so, if this will happen if t tends to infinite, positive infinite. Now if you tends t is to moving towards 0 from negative direction, in that case beta will tends to minus infinite, and this Ne would be e to the power minus infinite plus 1, so 1 by infinite is 0, so it will become towards the value of Ne, so u would become tends to Ne, right? So this is the case for if t is approaching 0 from negative direction. Now if t is moving towards minus infinite, so from negative infinite it's approaching, so in that case beta will moves towards minus 0, and the internal energy Ne would be e to the power minus 0 plus 1, so it would become e to the power 0 is 1, so Ne by 2, so you will become 0.5 Ne. Okay, so this is how the internal energy will behave for different case of the temperature. Now what you can do, you can basically plot these temperatures. Okay, plot the internal energy as a function of this temperature, so you will get the plot like this. So let's suppose we are plotting one direction you're plotting kbt by e, and one direction you're plotting u by ne. Okay, so now if you do it, so if it goes to -0, we know it is that it's 0.5 ne. Sorry, if it goes towards 0 from positive direction, it will becoming 0, so internal energy will be try to become 0. So it will move like this. This is, let's suppose 0 is, so it will move like this. Now if you move to the infinite, t to the power infinite, it will become 0.5 into ne, so it will try to approach 0.5 marker at infinite. Next is the t. If t approaches 0 from negative direction, then you will tends to ne. So ne means this 1. Okay, so it will try to become 1. Now if you move towards the -0, yeah, in minus infinite, it will try to become 0.5 ne, that is 0.5 mark here. So it will move like this. Okay, this 0.5 mark, this is 1 mark, and this is the temperature scale. So this is how the profile of the internal energy looks like for a two-level system. Okay, for different values of different sets of temperatures. Okay, and the last thing is basically the entropy thing. Okay, yeah. So the entropy expression you know is equal to u minus u0 divided by T plus Nk into ln Q. So now if you if you plug the expression of the entropy, expression of the partition function here, you will get entropy as Ne by T into e to the power beta e plus 1 plus Nk ln of 1 plus e to the power beta e. Now what will happen here is that, so if t tends to 0 and beta tends to infinite, in that case the entropy will also tends to 0. Now in another case where t tends to infinite and in that case beta will be tends to 0, in that case the entropy would be Nk ln 2. And lastly, if t temperature is tends to minus infinite and beta is tends to, in that case beta will be tends to 0 from the negative direction. That case also is b tends to Nk ln 2. Okay, now so here if you plot it, it will looks like this. So as you can see, unlike the previous cases, this is the 0. Yeah, this is the 0.5 mark. Okay, where this entropy is trying to approach for the case of positive and negative infinite. So here, as you can see, compared to previous behavior of the curve for other thermodynamic quantities, here for the case of entropy, as you can see, this curve is remain continuous. The entropy basically remain continuous at t equal to 0, which is not the case for the earlier, like for if you see the for internal energy at t equal to 0, there is some discontinuity happens here. Similar for the case of partition function also, there is this discontinuity was there, but for the case of the entropy, you can see this curve is remain continuous. Okay, this is one of the property. Okay, so let me write it. uh, Equal to 0 Kelvin. Okay. Okay. So now next thing that we are going to discuss is called the canonical ensemble. Okay. So the things whatever we are discussing is till now is the case of if the particles are non-interacting. Okay. So that means there is no energy transfers that is happening among the particles. Uh, but right now, for the case of canonical ensemble, we will consider that the system inside the system all the particles are interacting, and the energy is basically changing at every instant of the system. So we will use a different formalization to get the necessary thermodynamic quantities. Okay, so when the particles are interacting with each other, the energy will change at every instant. So we need a new formalization. So here the word the ensemble basically means is that the collection. Okay, so it's basically a collection of systems. Okay, in the context of statistical thermodynamics, the ensemble basically means is the collection of systems. So the concept is like that. So to basically set up an ensemble, what we do is that we take a closed system with a specific volume, composition, and temperature, and we replicate that particular system n times, okay, n numbers of times, and all of these identical copies of the systems, identical these closed systems, all of these closed systems are basically we basically therefore make those closed system basically thermally contact with each other. So that means they can also exchange energy, okay. So it's like this. So we first define a closed system with particular volume, temperature, and number of particles, NVT. These are fixed, okay. Now next will be we replicate the system. Let's call it n tilde number of times. So that means, and then what we will do, all these identical those systems are in thermal contact with each other. So that means that they can exchange energy. Okay. So the system, if how it's basically looks like, so it is looks like this. So let's suppose this is the system NVT with a particular system with particular number of particles, volume, and temperature. Okay. So this is the first system. Now like this we replicate the same system with the same specification. You will replicate one more times, two more times, three more times, like that. So like this way you can consider n numbers of time. 1, 2, 3, 4, 5. This is n number of times, okay. All of them have same specifications. NBT, 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 NBT. Okay. So now what we'll do is that, so each of these member inside the ensembles are also basically in thermal contact with each other. So they are all thermal. They all have thermal contact with each other. So that means they can exchange energy. Okay, and so that means the energy is not fixed. So for this system, let's suppose this member 1 has E1 energy, member 2 has E2 energy, member 3 has E3 energy at a particular instance. So like this. So although the NVTs are same, the composition, volume, and temperature, but since they are thermal contact with each other and they are exchanging energy by that, so the as a result, so their inner energy values are not equal. So next the thing is that, so let's we'll now consider, suppose Now, so that means that let's in so among n, so there are total in an ensemble n numbers of members are there. Okay. Now they are only differentiated by their energies, right? So out of this n number, let's suppose n0 number of members has in energy E0. So n1 number of members has energy E1. Okay, so like that. A similar way we have done for the distribution of particles in the energy levels. Okay, but here it's not energy level; it's the system itself. Okay, so N0 system has total energy E0, N1 system has total energy E1. N1 numbers of members that has their total energy E1, N0 number of members that has their total energy E0. So in this way we figure out the distribution of these members with different energies, and from this information we can get the weight of this configuration, right? So this is the formula is similar. So weight is we defined is like this: weight is n tilde factorial divided by n0 tilde factorial n1 tilde factorial n2 tilde factorial. So like this basically gives this the weight of that configuration. Okay, configuration is this basically. So now to find out which configuration is the greatest weight, we have to also consider here the constant in the total energy. So like total energy means total energy of the ensemble. Okay, so total energy of the ensemble that is remain fixed, that is E, that is N0 E0. So, so let's also give tilde symbol here also. N0 E0 plus N1 E1. So like this is the total energy of the ensemble. Okay, so now so this N0 N1 N2, so these all these values also are subject to this energy constant and the constant of the total number of members. So so from that, so similar way, so we can calculate the distribution of these members. Okay, so this basically this is subject to, so one is this constant and second one is the n equal to, so total number of uh, members is n0 plus n1 plus dot dot dot. So these two constraints are there. If you incorporate these two constraints, you'll get the distribution like the Boltzmann distribution that you got earlier. Ni tilde equal by n into e to the power beta ei. Ei is the total energy of that particular member. Okay, by q, and q is the ensemble partition function. Okay, that is summation over all possible energies inside the ensemble. Okay, so this is the, here Ni is the members. Okay, so the energy levels of those uh, group of members basically decides how the probability is to be on that particular group. Okay, so we got this partition function q. Now we'll calculate the internal energy. Okay, So first the total energy of the ensemble. Okay, not total energy. First we will discuss the average energy. Okay, so we will use the expression of the average energy here in order to get the expression of the internal energy. Okay, so the average energy of the member is E equal to E tilde by N tilde. So E tilde is the total energy of the ensemble, and N tilde is the total number of members inside the ensemble, right? So if you divided these two things with each other, then you will get the average energy of each of the member. Okay. So now, so after getting that, you can calculate the internal energy. So internal energy expression, internal energy U is basically equal to u0 plus E tilde by N tilde now. So from here we can write it in a different way. So we know E is basically total E tilde is basically summation over Ni by Ei by N. So average energy E is basically E tilde by N. So E tilde is nothing but Ni tilde by Ei tilde by N tilde. Okay. This is nothing but Pi tilde by Ei tilde. Now again, Ni tilde by N tilde, that is Pi basically is nothing but e to the power minus beta Ei by capital Q. Okay. So now if you substitute this thing here, you will get E as 1 by Q summation over I to the power beta Ei into Ei by T. Now you can write the derivative with respect to beta e to the power beta Ei as minus Ei into e to the power beta Ei divided by T. So if you substitute this thing here, basically it will make the whole expression in a very simpler manner. So if you do that, it will become E will become minus 1 by Q del Q by del beta. Okay, because it will be summation of it to the power beta E is nothing but Q, right? This thing, so we can write it like this. So E is become this. So this is the average energy of each of the member inside the ensemble. Okay. I can also write in terms of log, also logarithmic of term, also equal to minus del ln q of del beta. Okay, whichever way you find it easier. So if you have the energy of average energy, so from here also you can write the internal energy, right? So internal energy, u by u0 plus e. So u equal to u0 minus del 1 by q into del q del beta. So this is the internal energy expression. Okay. Okay, so now the next thing is the entropy. Okay, so the entropy is the same way. Uh, so here the entropy looks like this. So S is equal to Q minus U0 by T into plus K of ln Q. Okay. Similar way we get the expression of entropy for uh, for the for so simple systems. Okay, non-interacting systems for a single system. So similar way, using this total partition function, you can get the entropy. Similar type of formula here also. So get so for this canonical ensemble, we get the expression of entropy. Expression of partition function, and from there we get the expression of total energy, average energy of each of the members, internal energy, and as well as the entropy. Now we'll do some problem on that. First problem is for a two-level system, calculate the internal energy U and entropy S. So the information is two levels are E1 equal to 0 and E0 equal to 0 and E1 equal to E, and this level has degeneracy G0 and this level has degeneracy G1, and total number of is n independent particles. Okay, so you know the formulas. So total partition function Q is summation over Gj into to the power beta Ej, right? And here single particle partition function will be Q equal to G0 plus G1 into the power beta E, right? Now from here The total party, so the internal energy, the total energy is E equal to, minus del beta of ln q. Now total partition function q would be q to the power n, right, since the particles are independent. So for here, if you substitute it here, it will become n minus n into del beta of g0 plus g1 e to the power beta e. If you do the derivative, you will get n into g1 into e to the power beta e divided by g0 plus g1 e to the power beta e. This is the expression of the total energy. The next thing that you have to calculate is the entropy. So entropy formula we already know. Entropy is S equal to U minus U0 by T into plus kV into ln Q. Here also, if you substitute it here, here and here, so U minus U0, we know U minus U0 is this, basically U minus U0 total energy or the average energy E. So that is this N by T into G1 E to the power beta E by G0 plus G1 e to the power minus beta E plus kV ln Q. So ln Q, if you do, so ln is Q is nothing but, so N is there, so N kV. So N kV into ln Q, that is G0 plus G1 e to the power minus beta E. So entropy S. Okay, this is how you can solve this problem. Next, we will do a problem on three-level system with degeneracies. Okay, so now the similar quantities we will calculate. Zero E and 2E. So the degeneracies G0 has 1, G1 has 2, and G2 has 3. So these are the degeneracies. And the partition function, if you want to write, it will look like this. Q will be equal to, we know, for a single particle partition function, summation over Gj to the power beta Ej. So it will become G0 plus G1 e to the power minus beta E, right? So similar way, internal energy U, so U is same, so minus del beta of capital Q If you calculate this, it will you get n into 2e into e to the power beta e plus 6e into e to the power 2 beta e divided by 1 plus 2 e to the power beta e plus t into to the power minus 2 beta e. Okay, this is the internal energy expression. Next is the entropy. Entropy we know expression is u minus u0 by t plus kb ln q. It will give you n kb ln q plus beta 2e to the power minus beta e plus 6e to the power 2 beta e divided by q. Okay, so this way you can calculate the entropy. The last problem that we are going to discuss is about the 1D quantum harmonic oscillator. Here also similarly we will calculate the to energy level. From there we will calculate the partition function and we will calculate the entropy. So for energies are basically En equal to h cut n plus half, we know. So here in this case q would be one particle would be, so let's suppose degeneracies are 1, so gn is equal to 1, n can be 0 1 2 3, so all the levels of degeneracy 1, so e to the power beta en, so it looks like this, e to the power beta h cut h omega n plus half. If you take it to the power beta h cut omega as common, no, e to the power minus beta h cut omega half as common, then it will give you e to the power minus beta h cut omega to the power 0 plus e to the power beta h cut omega to the power 1 plus e to the power minus beta h cut omega to the power square plus dot dot dot, like this way you can expand. After doing that you will get e to the power beta h cut omega by 2, so this will like x, so 1 plus x square plus this, then after doing the summation you will get to do the summation, this is summation of infinite series, you will get e to the power beta h cut omega by 2 by 1 by 1 minus beta h cut omega. Okay, so this is the expression of the partition function q. So now you get the partition function q. Now from here similar way, u is basically E is basically minus del beta of ln q. If you do that you will get h cut omega by 2 plus h cut omega by to the power beta h cut omega minus 1. Okay, and the last thing is the entropy. So entropy, if you calculate you will get kb beta h cut omega divided by to the power beta h cut omega minus 1 minus ln 1 minus e to the power minus beta h cut omega. Okay, this is the way you can calculate the internal energy and the total energy and the entropy of the system. So that's it. So now end the class.